Have you ever wondered how design blueprints are translated into actual software components? Well, that's where implementation modeling in object-oriented analysis and design, or OOAD, comes into play. This process is a crucial step in the software development lifecycle. It's like the architect's blueprint for a house, providing detailed low-level specifications for how the system's elements should be constructed, integrated, and deployed. In essence, it bridges the gap between design and coding. This is where the rubber meets the road, where abstract design models evolve into concrete software components. It aligns closely with the architecture and design established in earlier stages while setting the stage for actual coding and development. So, if you're intrigued by the process that ensures your design blueprints don't just stay as mere diagrams on paper, but come to life in the form of functional software, then you're in the right place. Without further ado, delve into the fascinating world of implementation modeling. The first step in implementation modeling is class and object design. This is where we bring to life the blueprint of our software, translating abstract ideas into concrete structures. Let's start with class definitions. A class is like a blueprint for creating objects. It outlines the attributes or properties and methods or behaviors that an object of this class will have. For instance, if we're building a car simulation, we might have a car class with attributes like color or speed, and methods like accelerate or brake. Then we have object instances. These are individual occurrences of a class. Using our car analogy, if the class is the blueprint, then an object instance is the actual car built from it. Each object instance has its own set of attribute values, but the methods it can perform are defined by the class. Now let's talk about encapsulation and access control. Encapsulation is a fundamental principle of object-oriented design. It's all about hiding the internal workings of our classes and objects, exposing only what's necessary. We use access modifiers to control this visibility. For example, a private attribute can only be accessed within its own class, while a public one can be accessed from anywhere. Why is this important? Well, encapsulation ensures that our objects are like black boxes. The outside world doesn't need to know how they do what they do, just what they can do. This makes our code easier to understand, less prone to bugs, and more flexible for future changes. So, class definitions provide the blueprint, object instances bring it to life, and encapsulation and access control ensure it's well organized and robust. Together, they form the foundation of our code, a solid structure upon which we can build. With a clear understanding of class and object design, you are ready to assemble these into larger components. Now that we have our classes and objects, it's time to assemble these into software components. Imagine the components as the building blocks of our software. They're the tangible pieces that, when connected, form the functional whole. This assembly process is critical because it ensures all the elements of our software work seamlessly together, creating a coherent, efficient system. One tool that aids us in this assembly process is the component diagram. These diagrams are like detailed maps, illustrating how various software components fit together. They visualize the dependencies between components, the interfaces they expose, and the data flows that connect them. These diagrams are essentially the blueprints of our software construction, guiding developers as they piece together the components into a cohesive system. But it's not just about fitting pieces together, it's also about organizing them in a way that makes sense. That's where package structures come into play. By organizing classes into packages or modules, we create a structure that promotes modularity and maintainability. Think of it as arranging books on a shelf. You wouldn't randomly scatter them around. Instead, you'd group them by genre, author, or topic. Similarly, package structures help us group related classes together, making it easier to manage, update, and understand our software. So we have our component diagrams like architects' blueprints laying out the structure of our software. We also have our package structures like librarian systems, categorizing and organizing our classes. With these tools, we can assemble our software components effectively, ensuring they function as a cohesive and efficient system. But remember, software construction is not just about assembly. It's also about ensuring that the components interact with each other in a logical and efficient manner. And for that, we need to look at the sequence and control flow, which we'll discuss in the next segment. With all components assembled, we can now focus on the sequence and control flow. Sequence and control flow define the order of operations. Imagine a symphony orchestra. Each musician knows their part, But without a conductor to guide the sequence and pace, the performance would be chaotic. The same principle applies to software development. Sequence and control flow are our conductor, dictating the order in which operations occur and how the control passes between different components in the system. One of the key tools in outlining sequence and control flow is the sequence diagram. This diagram is like a musical score, detailing the interactions among classes in terms of an exchange of messages over time. It specifies the order of operations and method calls for key functionalities or use cases. For example, when a user logs into an application, the sequence diagram would illustrate the steps involved, from entering the username and password, to the system validating the credentials, and finally, allowing or denying access. Another vital tool is the activity diagram. This diagram is akin to a choreographer's blueprint for a ballet. It describes the workflow and control flow within specific processes or business logic. It's not just about what happens, but also when and under what conditions. An activity diagram might illustrate how an online order is processed, from the moment the customer clicks buy to when the order is dispatched for delivery. Both sequence and activity diagrams are incredibly useful for understanding how a system behaves and for ensuring that all scenarios have been considered. They provide a visual representation of the process, making it easier for developers to understand at a glance. However, it's important to remember that these diagrams are not set in stone. As the system evolves and changes, so too can the sequence and control flow. They should be reviewed and updated regularly to reflect the current state of the system. Having established the sequence and control flow, we can now focus on how to manage data. Data management is crucial in any software development process. It's like the engine room of a ship powering the entire operation. In the world of implementation modeling in object-oriented analysis and design, data management primarily involves three key components. Firstly, we have the database schema. This is essentially the skeleton of your data. It defines the structure of databases, tables, relationships, and constraints. A well-designed schema not only optimizes data access but also ensures data integrity. Next up is Object Relational Mapping, or ORM. This is the magic that connects your objects in code to entities in the database. ORM allows your software to create, read, update, and delete records in your database using object-oriented languages, making data manipulation more intuitive and less error-prone. Finally, we have data access methods. These are the rules of engagement for how data is retrieved, modified, and stored. These methods also handle important aspects like transaction management and concurrency controls, ensuring that your data operations are safe, efficient, and consistent. In essence, data management is all about maintaining balance and harmony in the way data is handled. It's about ensuring that data flows smoothly from your database to your objects and back, while keeping everything organized, secure, and efficient. With data management in place, we can now focus on deployment and configuration. Deployment and configuration is the final step in implementation modeling. This is where all the pieces come together as we translate our theoretical models into a practical, functioning system. Deployment diagrams play an essential role at this stage. They provide a visual representation of the physical deployment of software components onto hardware infrastructure. This includes the layout of servers, databases, and networking components. These diagrams help us understand how our software will interact with the underlying hardware, and they guide us in distributing our software resources efficiently across the system. But diagrams are only half the story. Configuration management is the invisible workhorse that keeps our software functioning smoothly. It involves setting up environment-specific settings, build parameters, and dependency management. These configurations ensure that our software components interact correctly with each other and with the system environment. Think of it like setting up a new home. The deployment diagram is your blueprint, showing where each piece of furniture goes. Configuration management, on the other hand, is like deciding on the settings for your appliances, ensuring that they work together seamlessly. This stage requires careful planning and execution. Any mistakes here can lead to system instability or even total failure. But with a well-designed implementation model, you can minimize these risks and ensure a smooth deployment. With all these elements in place, you now have a comprehensive understanding of implementation modeling. So, we've come a long way in understanding implementation modeling in OOAD. We delved into the process of turning design models into executable software, discussing its key components like class and object design, component assembly, sequence and control flow, data management, and deployment and configuration. We've learned how these steps provide clear guidance for developers, ensuring consistency with design and facilitating testing and debugging. Furthermore, we've seen how a well-modeled implementation structure not only makes the software easier to maintain, but also improves its longevity. Remember, it's vital to align your implementation models with your design models, promote modularity, and follow standard conventions. These best practices will help you create robust, efficient, and maintainable software systems. Remember, implementation modeling in OOAD is a critical step in turning design blueprints into actual software components. Thank you for joining us on this journey.